Okay. See, I know that there are this month actually some sessions are actually little bit hectic actually due to some that Revit sessions could not be conducted within the time. So, but yes, consistently you start study actually. See, there is no hurry in learning actually. It's a continuous process. So for this month, actually bear with this. Once the Revit sessions are over, then it will be smooth again. So till then, at least how much time are you giving for study actually daily? कितना time दे रहे हैं आप study को?
So 4 to 5 hours.
Okay, okay, that's good number actually. It's very good number. Those who are not able to do more time, at least spend 1 or 1.5 hours a daily actually. So 2 hours is our session generally, and 1.5 hours for practice. That is also enough. But all of you should be consistent for on that. Then it will definitely give the results. Okay, so let's start today's session. Today we will learn the design of bending member. So what is bending member? Anybody knows what is bending member? That we are going to use the steel material. What is bending? So we know that if there is a beam or any member, and if you apply the load out of plane load, so you know that the axis of the member is this, but your load is perpendicular to this axis. That is, we can say out of plane load, and this will cause the bending of the member. So it will bend. It will try to deflect like this. We call it as a bending. And if there is a bending in any member, what happens in that member? What forces we get in bending? Yes. Let's say this is a beam supported on one pedestal. So due to the load, what will happen to this? If there is a load on this beam, so this will try to bend. Yes,
Yes.
it will bend. And due to the bending, what forces are coming in this?
So at the lower bottom side, there will be tension in the fibers.
And at the top side, it will
It
be
will be
compression.
compressed.
And the couple form, we call it as a bending moment. If it is a compression and let's say it is a tension and there is a distance between the two forces, D. So this couple forms the moment, we can say. So that is the moment actually. So this moment we call it as a bending moment. Okay. So actually it is a resistance, but due to the load, it will have a bending moment, and to resist the bending moment, there will be internal compression and tensile forces. Okay. So this is a bending. So generally it happens if the load is like this. If I ask you, let's say this is your column. So does the column, can we say column as a bending member? Let's say if this is the only load in the column, can you say this is a bending member? Yes. Can I say this is a bending member? First case. Then second case is I am having load like this. So can I say this bending member? So case one, case two. Let's say I'm having one more case. So tell me which one is bending member and which one is not. Let's say I'm having the column and I'm having a moment applied at the end. So this is your axial force, then this is your horizontal force. Okay, and then let me take one more example in which this is your column and we are having one load like this, one load like this, P and H. So tell me which is a bending member and which is not. So all of you know that beam is bending member. This is very clear from this. So can you say this case 1 is bending member? Yes. Any guess?
So it will buckle.
Yeah. So whenever say it will buckle, we don't say it is a bending member actually. We call it as an axial force member only, because we don't allow buckling in any columns. That means before buckling, we are designing in a such a way that it will not buckle. That means if it doesn't buckle, then we can say it is axial member, axial force member. And axial forces are either it may be compression or tension. So in this case, it will be compression. So it is a column. I will call it as a column. This member I can call it as a column because it carries only compression. Can you tell me what is happening here? What is this? Is this column or beam? So this is a column because it is having orientation vertical, but it is the force is horizontal, right? So definitely you know that due to the horizontal force, there will be bending moment in this column. So there is no
Yes.
axial force in this column. Ideally means there is axial force due to self weight, but it is very less. But due to this horizontal force, it will bend. So this is a column, but it has a bending moment. So let's say self weight is P here. Then I can say this is a column also plus bending member. It is a combination of the two, right? So means axial force plus bending moment, axial plus bending. So both forces are there in this column. If you consider this case, third case, what is this? It is a column, definitely yes, due to its orientation, vertical, but it will carry bending moment, bending. So it will carry bending, and if you consider the self weight, then it will carry axial force also. So it is also column with bending and axial force. And if you take this case, it is also same. It is a column and it carries due to P, it will have axial force, and due to H, it will have a bending moment. So bending. So does this, can I say this as a column? Oh, let me delete this first. Can I say this as a column?
No, sir.
Yeah, because there is no axial force in this beam. There is only out of plane load due to which it will bend. And I can say this as a beam. So this is a beam. Now, if I ask you if there is a horizontal load like this, so is it a beam?
Yes, sir.
Yeah, it is a beam, but it is carrying axial force. So I can call this beam as a column also. See, please try to understand. Column means as far as the behavior is concerned. The name doesn't matter actually many times. Or I can say horizontal column. See, many times these kind of terms are not used, but as far as behavior is concerned, it is carrying axial force and bending moment. So it is a behaviors like a column. So there are actually three terms we use. If there is no horizontal force and only bending moment, then I can call this as a beam. Okay. So this is your beam member. Now this is your column because it is carrying only axial force. So this member is column, and the member which carries axial force also and bending also, this one. So this generally in steel structures, we call it as a beam column. So it is a combination of beams and column both. That's why we can call this as a beam column. So the behavior is beam column. Beam column means it carries bending and it carries axial force also. Okay. So these are the terms generally used in steel structures: beam, column, and beam column. Okay. So there are certain structures which are having like this inclined columns. Due to the inclination, there will be uh, axial force also here, and it will cause a bending moment also. So this we can call it as a beam column, or I can call it as a strut. Strut is nothing but a column itself, which can carry axial force and bending moment. Now today we will start with the design of bending member. That means there is only bending moment and there is no axial force. So it is a beam. So we will how to design the beam. Let's see. in detail. So what forces are coming in the beam? We have already seen bending moment. We get the bending moment M, BM, which is causing the compression and tension in the member. Top chord compression, bottom chord tension. Say when I say it is a simply supported, then and then this is the case. If it is a fixed beam, then fixed beam में कैसे forces आएंगे? Let's say this is a fixed beam. Then we know that our bending moment diagram for the fixed beam is like this. Correct. So this is your bending moment. That means there is a tension here, compression here, and as the bend moment is here at the top, so there will be tension at the top and compression at the bottom in the support zone. Similarly here. So please try to understand it is not always compression at the top. If the bending moment is like this, then it will have a tension at the top. And that is also different for cantilevers also. Now, if you look at this closely, then there is a compression, there is a tension. And all of you know that how to design the steel members for compression and for tension. So what is the peculiarity of compression? Compression ki peculiarity in steel design, what is that peculiarity? If you want to design any member for compression, what we do? How we get the permissible stresses in compression? Axial compression I am talking for the time being. It depends on L upon R, that is slenderness ratio, R minimum. And it also, so this is the peculiarity. So it is something that means even for this beam, as this top chord is carrying compression, it may buckle. And as it may buckle, that means it may depend on slenderness ratio. So that is the peculiarity. For tension, what we do? Tension, there is no problem regarding slenderness. We can directly take the stresses 0.6 Fy. See, this is, I'm just telling you conceptually first. But there are certain differences in design of beam. So if you want to design the beam, then for tension, so how we design here in axial force member like columns, we calculate the axial stresses sigma AC, which is P by A, axial compressive stress. If there is a tension in the member, then we calculate sigma AT, which is tension divided by area, cross-sectional area. Now in bending beams, there is a bending moment. So what kind of stresses comes in the bending member? Sigma B, bending stress. In column, it is axial stress, but in beam, it is a bending stress. But there are two stresses. One is the compressive stress and second is the tensile stress. So there is a sigma BC, which is nothing but bending stress in compression. And there is one more stress in the beam, which is sigma BT, that is bending stress in tension. So whenever we calculate these stresses, see how to calculate bending stress. You know the bending moment divided by Z. ZC means Z value on the compression side, and there is a M upon ZT, okay, which is on the tension side. So Z we can calculate, all of you know how to calculate Z. Z we can calculate by, let's say this is your I section. So Z is nothing but I upon Y. So if you want to calculate the top side Z, for our problem, this is compression phase and this is tensile tension phase. So let's say this is YC and let's say this is YT. So ZC will be I upon YC and ZT will be I upon YT. I is same for the cross section. Property is same. Moment of inertia is same. Now I will ask you one fundamental question, that let's say you have a I section like this. For simplicity, I am just taking this as a rectangular part. Generally, there is a curvature. This is your I section. And let's say I'm putting one more plate over here, additional plate. Generally, we call it as a plate girders. Now tell me if I calculate the neutral axis for this. So this is your center of the I section actually. So will your neutral axis be below this line or above this line? Neutral axis कहाँ रहेगा इसका?
Below this line.
Below this line, because see there is more area available at the bottom. So our actual neutral axis will be here, near to this. So that means your this YT value is there and there is a YC value here. So this is a compression zone. This is, that means ZC will be M upon YC and ZT will be M upon YT. So which value will be more in this case? ZC ज़्यादा रहेगा या ZT?
ZT.
So this will be more. So definitely where we many times we require more Z. So if you are expecting Z more at the tension phase, then you can increase the, you can add the plates here. But generally the design is governed by the compression. So you can add one or more plate over on the compression phase also. Okay, so this is the general case. Okay, now in the design, now there is a bending stress in compression, and we know that if there is a compression in any member, then it depends on the slenderness ratio. So if you want to calculate the sigma BC permissible, if you want sigma BC permissible, permissible stress in bending compression, it depends on slenderness ratio, which is L effective upon R minimum. And one more term is there in beam design. It also depends on D upon T ratio. So D is the depth of the beam. Okay. And T is the thickness of flange. So let me show you this. If this is your I section, for example, and this is your web, this is your I section. So what is D? So this D, capital D, is nothing but overall depth of the member from here to the bottom. So this is your D, and this is nothing but thickness of the flange. So you know that this is your flange. So TF. Okay, so this is, so D by T means this ratio. You can get this D and TF value from the steel table. You know how to get the L effective values, and you know R minimum we get from the steel table. So, and we get this permissible stress from the IS code, IS 800. Okay. So that means in beam, compression side is governed by the L by R and D by TF. And if you say sigma BT permissible, so as there is nothing, no compression, it is purely tension, then there is a constant value for permissible stress in bending tension, which is 0.66 Fy. Okay, that's as per the code. So if you are designing beam for tension side, you should check this stress. If you are designing compression side, then you should take these stresses from the table, right? Depends on lambda and D by TF. Now let's see the design of the beam first. So we know that these kind of loads are there in beams. Now bending, maximum bending stress allowed here is either sigma BT or BC, both actually. These are maximum permissible. But sigma BC depends on the L by R, 0.66 Fy. So in tension, actually, what was the stress, permissible stress? Yesterday, what we learned? For tension, it is only 0.6 Fy, but in bending, it is little more. Okay. Now let's take one example here. Let's say we are having a structure like this. 6 columns are there, and they are connected by the beams. So there are these beams. It can be, say, we can say it is one room of 4 meter width. and this 4x4 room is there, and there are 6 columns and one beam is there here, and there is a load which is here like this, and I can assume this load to be floor load. Let's say this floor load is 2 kilonewton per square meter. Our problem is design of bending member which is laterally supported. Okay, laterally supported means, let's say this is a slab. Okay, so if it is laterally supported, then I can say that it is fully restrained, and if it is a fully restrained, then permissible, this value sigma bc also I can take at a 0.66 fy. If it is not buckling, correct, if you can assure that the beam is not buckling in compression, then you can say I can take this value as a 0.66 fy, sigma bc permissible. Now why it is not buckling? So you know that for on the beam there is a load like this, and this goes in compression, this flange and this flange will go in tension. So for tension flange there is no problem, but this compression flange may buckle like this. So it will try to go like this. So this kind of buckling is possible here in your beam due to compression load. So you can understand, you can imagine this. If you are applying load and there will be compression in this plate, so it will try to buckle, means it will try to go laterally, buckle, lateral buckling we can say. Now if, how can you restrain this lateral buckling? कैसे करेंगे? Let me draw over here. Let's say this is your buckling. After load, after buckling, let's say the beam buckles like this. Now you can understand. This is buckling. This is a compression part. That is why it is buckling. See, tension face is, tension flange is not getting buckled. So the original position is there for this. Now, if it is laterally buckling, so how can you restrain? Means how can you resist that buckling?
Additional section.
So no, you can support this like this. You will provide certain support over here. If you give support here in the lateral direction, then it will not buckle. So
Stiffness will be.
yeah, stiffness or lateral buckling. So I will show you. So in steel structures, we know that generally there are slabs. When there are slab, I'm saying, let's say I'm putting one slab over here. So for this room, this slab is there. That means slab is supported on the beam B1. So let's say I'm having one slab over here. And let's say I'm putting one shear connector to this point. I'm putting these bolts. I can call it as a shear connectors. I will weld this to this member and then I will anchor this into the slab. Now, if there is a vertical load, will it buckle in this direction? Yes. This slab will give the support to this. That means it will not buckle. It will not buckle. So we generally call this term as a, it is restrained. It is restrained in lateral direction. As it is not buckling, definitely I can take the permissible stress, full stress. So in that case, it will be sigma BC permissible 0.66 Fy. Okay. So it is as good as a tension, means exactly same as tension member. And you can see in the code also, I think I have shown that to you. Here you can see sigma BT or sigma BC 0.66 Fy. So now let's design this member. So how to calculate the load on the beam? B1, half load will go on B1 from here, from this slab, half will go from this side. I think all of you know that this, how to calculate the loads and everything, you know. Half from here, half from here. So how much is this half? 1 meter. How much is this half? 1 meter. So total is 2 meters. And what is the slab load? 2 kilonewton per square meter. So 2 into, So from one slab it is 2 kilonewton, or you can directly calculate. You can take this 2. So this 2 into 2 will be 4 kilonewton per meter. Okay. Half from this, half from this. Here actually half load is calculated. Is it clear, load path?
Yes, sir.
Now, then means we get this 4 kilonewton per meter load on the beam. Then you can calculate the bending moments, which is WL square by 8. Assume the beam as a simply supported. The moment is WL square by 8, 4 into 4 square by 8 kilonewton meter. And there is a shear force also, which is WL by 2, which is also 8 kilonewton. Shear force also you know how to calculate. This W into L by 2. So there will be a reaction over here, 4 into 4 by 2, which is 8 kilonewton. This reaction is nothing but your shear force. So this you know, I think. Now, whenever we design any member, we have to assume certain sizes, and then we check for the stresses. If the stress is less than permissible stress, we can accept that the section is safe. If the stress is more than permissible stress, then we revise the section to the higher side. So that is the philosophy of design. So I think all of you know this. For this problem, let's assume ISMB 150. We will use this for beam design. So the weight is this given in the code. D is 150, capital T is 7.6 mm. Capital T, all of you know, thickness of flange. Then small t is thickness of web. So this capital T is thickness of flange. Then this is a small t, thickness of web. In steel table, there is a small t and capital T only. But this small t means TW, means thickness of web, and capital T means thickness of flange. Then we also get the I values, IXX and ZXX values from the steel table. So you can refer the steel table IS 800, 808. Now, what is the permissible stress in bending? 0.66 Fy, 0.66 into 250 is 165 Newton per mm square. Now, how to calculate the actual stresses? Sigma BC calculated is M upon ZXX. M by Z we have already seen. As this ISMB section is symmetric section, ZXX and ZYY both are same. So I can take any value of those. M upon Z will be 82.55 Newton per mm square, which is less than permissible stress. That means your section is safe. So there is one more term I will tell you. So there will be shear force in the beam, and due to the shear force, there will be shear stress. So how we calculate shear stress? Tau V is equal to V upon dt. So all of you know that who is resisting the shear in beams? कौन resist करता है shear? Who takes the shear in beams? The web. So web is taking the shear. So resistance is given by the web area. Web area is how much? This T value, thickness of web, and this depth of the web, which is this. Let's say dW, depth of web. So tau is equal to V upon area of cross section, that is area of web, let's say. So area of web, now let's go to the problem. V upon dt. So dt, you know, here they are taking, you can subtract the flange thickness if you want. So 8 upon dt, T is the thickness of web. So 11.11, and the permissible stress in shear is 0.4 Fy. So tau V permissible is, so this is your tau calculated from the analysis, and there is a tau permissible value, which is 0.4 Fy as per the code. 0.4 into 250, 100 Newton per mm square. Clear, all of you? Permissible stress in shear. To calculate the shear stress, actual shear stress is this tau VA, and permissible is 100, less than 100. So this is safe for shear also. Now in design, we check the stresses, we calculate the stresses and check with the permissible stresses. What else we need to check in beam design? बीम डिजाइन में और क्या चेक करते हैं हम? We check the deflection also. So deflection is also very much important in any design of beams. So in beam we design for strength, that is stresses, and we also check it for deflection. So we should calculate the actual deflection. So you know that for simply supported beam for UDL, the formula for deflection is 5 WL raised to 4 upon 384 EI. So 5 into W here into L raised to 4 divided by 384, and E value for steel structure is 2 into 10 raised to 5. Okay. So try to understand. 5 W is small w, L raised to 4 upon 384 EI. So E value for steel is 2 into 10 raised to 5 Newton per mm square. I value we get it from the steel table IXX. This I is nothing but IXX. Steel table. So the deflection is 9.17. And what is the permissible deflection in steel structures in beams? L upon 325. So span of the beam is 4 meters divided by 325 is 12.3. So it is safe for deflection also. This is nothing but serviceability criteria. See, we are designing the structure by working stress. Please try to understand. This is serviceability criteria. And the stress was the strength criteria. So this, whatever we are doing regarding the stresses, it is a strength criteria. So in design, these are the only criteria actually, nothing else. So I hope you got this concept. Got it? Hello?
Yes, sir.
Okay, now we will switch to the next problem. Yeah. So same problem I'm taking, but in this case, it is laterally unsupported. So let's say there is no slab, or there is a slab, but I'm not connecting that slab to this beam. So I will not provide these shear connectors. So the problem is that I'm not providing this. There is a slab, that means slab will transfer the load on the beam, but this is free to move in this direction. So this beam will buckle, right? Because I'm not connecting this to the slab. So there is no restraint here. So last time that means it may buckle like this, like this. It will buckle like this. As it is buckling, that means we should now take care of the compression part. So the permissible stress in compression will govern by the buckling, that is slenderness ratio. So the problem is same, the load is same. That means bending moment will also be same, shear force will be same. Only the permissible stresses are different in this case. So in this case, I'm taking the section as ISMB 200. So I have written the T thickness of flange, capital T 10.8 from the steel table, thickness of wave 5.7, IXX value, ZXX value, RYY value. You know that RYY is minimum in general. So this is your RYY, which is minimum, R minimum. Then there is a H2, H1. Okay, that we will see. Yeah, there are some other values also. So if you want to calculate the permissible stresses in compression, then it depends on the D by T. So D is the overall depth of the beam. I will tell you kya hai. Oh, let me go into the steel table itself. क्या हो रहा है? Okay, let's go to the problem. I don't know. So here d by t, thickness of flange. Then there is a t by t. So capital T is the thickness of flange, 10.8, and small t is the thickness of web. We get it from steel table. So we found these two ratios. Then there is a d1 upon t. So what is d1? Let me tell you. We have open हो रहा है कि नहीं? ठीक है. So generally we have the I section like this. There is a curvature here. Then we have again curvature over here. And again here curvature, curvature, again curvature. So there is a radius actually available here. So you can get this. So एक minute. क्या हो रहा है? So this H2 is 2 times H2 means we are interested in this value actually here. This is your D, this one D1, D minus this capital D minus these thicknesses, right? 2 times H2. Getting this?
Yes, sir.
So this is D1 and D1 upon T is the thickness of web, small t. So we get these ratios, this one, and there is a L effective upon R minimum. Okay. So RYY, L effective, we can consider this as a hinge as we are considering the beam as a simply supported. So L effective will be L only, right? So that's why we are taking here 4 meter itself, L effective. And R minimum is 21.5. So these are the ratios we get. Now you can go into the steel table. Steel table open hoga क्या? हाँ. Now in steel table, if you go for the design of beams, can see the table 6.1a, maximum permissible bending stress in compression, this sigma BC in equal flange I beams or channels. So our I beam is there. Now here there are different ratios given, T upon T, small capital T upon small t. If it is greater than 2, then you use this table, and D1 upon T should be greater than 85, then you can use this table. So what is our T upon T value? T upon T in our case is so it is not more than 2. So there is next table. T upon T less than 2. So 1.8 is our T by T value. So we can use this table for the time being. Now check D1 upon T. So D1 upon T हमारा कितना है? 26, which is less than 85. Now I can use this 6.1b table. Now go for D upon T ratio. D upon T is 18. So here it is 18 point something here. So I will consider this part. And what is L upon R value here in this direction? L by R is 186. So ये कहाँ आएगा मेरा? Somewhere here in this direction. And 186. So here, so it will be, the value will be near to 99, but we can interpolate because the values are not exactly 18. So let's see, go into this table. Now here 18 and 20, it is between 18 and 20, and it is also 186. So it is between 180 and 190. So you can interpolate by that normal procedure, and you can get the permissible bending stress. So see 18.518 is between 18 and 20, and 186 is between 180 and 190. So this is the our expectation of this value. So through interpolation, you get sigma BC is 95. So you know these values 99, 94, 91, 95. So it will be somewhere in between the two, which is 95, which is okay. So we got sigma BC 95. So now you can say due to the buckling, the values got reduced. In the previous case, when the slab was giving the restraint to the beam, we have taken this sigma BC as directly 165 value, 0.66 FY. But in this case, it is possible that it will buckle, so it got reduced, which is clear from the steel code. Now you got the permissible stresses. Now calculate the actual stresses M upon Z. You know M, you know ZXX values. So this is 35 less than 95. See, we are comparing with 95 here in this case. Now it is safe. Check for shear is same as the previous case, V upon dt less than 100. And deflection also same, L upon 325 permissible deflection. And this formula, actual deflection. Actual deflection less than permissible, safe. Got this?
Yes, sir.
Now there are these point load problems are given here. So many times what happens, if we have now look in the plan. This is a plan, let's say, and we are interested in the beam design. So see our this is our beam design under consideration, and let's say we are not giving any shear connector to this slab for the time being. Let's say still I want to design this beam B1, let's say, but you can say there are secondary steel members which are connected to this. Okay. And what is the spacing of these secondary beams? 1 meter, right? So even though slab is not giving any restraint to this beam, but these secondary beams are giving here. So if you draw the, we can say section like this, then you will see that, let's say this is my I section, main beam, our main beam. And let's say I'm connecting this secondary beam. This is your secondary beam, SB. And let's say this is your main beam. We are designing main beam in this case. So many times we can connect. So this is also, let's say, your I section, which is connected to this welded or bolted, whatever. Now, this beam is connected by these secondary beams. This is your main beam. That means in this case, your effective length will be between the two, because if this main beam tries to buckle, it will buckle like this. For example, I'm just giving example. So it will buckle. That means your main length is this 1 meter and not 4 meters. Try to understand. Getting? So your L will be 1 meter. Then L effective, you will give some coefficient for this, let's say 0.85 L. So it will be 0.85 into 1, let's say, for example. So only L upon R calculations, you will take this L effective as this one, which depends on the L, which is 1 meter. Have you got this?
Yes, sir.
All other design parameters are same. You need to calculate the bending moment. In this case, as there are point loads on the beam, you can calculate the bending moment like this. You will draw the loading diagram like this and get the bending moment values by using principles, basic principles. All other things are same. Only you need to go for the L value as 1 meter. Got this? And if there is a point load, then deflection formula is different. So I think we will share this to you, how to calculate the deflection for beams which are having point loads. So there are different formula, which are ready-made formula are there actually available. You can get it on the internet also, and we will share also on the classroom. So that is the only difference. All other parameters are same. Only L will be this one. Now I ask you one question. Let's say if this slab is also giving restraint to this. समझो मैं यहाँ shear connector लगा रहा हूँ. Now tell me what sigma BC permissible you will take. If there are shear connectors connected to the slab, to this beam, what will be this value? As there is a full restraint, definitely I will take this value as 0.66 Fy, which is 165. That's it. Even though these beams are connected here, but actually the full restraint is there due to the slab by using these shear connectors. So as it is fully restrained, I can take full stress. If it is not restrained, then I will take this value as L. I will calculate L effective as 0.85 L, which is 1 meter. And then I will calculate permissible stresses from the code, which depends on L by R, L effective upon R minimum, D by T, then that capital T upon T, and D1 upon T. There are 4 ratios on which we can get the permissible stresses. So I hope you got the design of beams. समझ में आया सभी को?
Yes, sir.
Any questions, all of you? Now we will switch to the next problem, which is a beam column. Only column design for axial force we have learned yesterday, which is a design of compression member, purely axially loaded. So it may be compression member like column with axial load, or it may be trusses having compression. Now we will see how to design a beam column. So beam column. Now you know what is meant by beam column. The beam column is nothing but carrying the bending moment and axial force. अविनाश नहीं आया क्या? Okay.
No, sir.
वो अभी रेविट और ये करके करके तंग हो गए ठीक है. Now let's say we are having one frame. So generally we find this kind of structures in buildings. It may be RCC building or steel building. So we are concerned with the steel structure here. So the portal is there. Let's say we are having steel beam, steel columns, and due to the vertical loads there will be bending moments in beams and there will be bending moment in columns also. Apart from that, in columns we have axial force P. Whatever is the reaction coming from this beam, it will transfer in the column as axial force. So it will be P and there will be bending moment M. So in this column there is axial force and there is a bending moment. Now let's say this P value in the column is 200 kilonewton and moment value is 20 kilonewton meter in column, and we want to design this column. So we will take maximum moment. Actually there is moment at the bottom also, but we will design for maximum, then there is no problem. So can anybody tell me how will you design this? So due to the axial compression force, what will happen? There will be axial compressive stress sigma AC. I have to calculate P upon A. A is the area of column, cross-sectional area of the column. P is 200 kilonewton. So this is your axial compression stress in column. Calculated means we are calculating this from the analysis. Due to the bending moment, there will be bending stress in compression M upon Z. Getting?
Yes, sir.
So we get this value stresses. Now we know that how to calculate the permissible stresses. If it is axial compression, how we calculate it? Permissible stresses. Sigma AC
0.6 F.
permissible, how we get? No. Sigma AC permissible. Compression, don't forget. If it is a compression axial force, L upon R minimum. It is exactly compression member design because it is axial stress, this one.
Yes, sir.
And
Yes.
where we
Got
get
it.
these values? Yeah. So what will be the L effective for this? इसमें एक्सेल का दिया नहीं क्या? Sigma AC cal and sigma AC permissible. Okay, so sigma AC permissible we get from that compression member design only. Okay. So ये पता है ना, sigma AC permissible we can get it from the IS 800 compression design. We have seen yesterday. कहाँ है वो? This table. Sigma AC permissible. L, it only depends on this lambda. L by R. Fy. This is 250 and L upon R कितना आ रहा है हमारे प्रॉब्लम में? L upon R 89 आ रहा है. So L effective we calculated by वो 0.3 meter into effective length we can take 0.85 comfortably. So 0.85 into 3 meters will be L effective and R minimum as per the cross section properties. Then sigma AC will be 90 here. So how we are getting 89K with respect to 89, it is somewhere near 90. So this is 250 and this is 89, means let's say it is near to 90 we can say. So it is 90 that we are getting. So sigma AC permissible is 90 from that table of the compression member. Now there is a bending moment also. So bending moment permissible stresses, how we get? We have just learned it. It depends on D by T, L by R, then T by T, D1 by T. And that table 6.1b. And you get the permissible stresses for bending compression. So sigma BC permissible is 131. So these are the two things. Now there are two stresses, one is bending stress and one is axial stress. So as you know that if there are two different forces in the same member, then there is the interaction between the two. So this is the interaction, sigma AC calculated divided by sigma AC permissible. Then there are some factors CMX and this given here, and the ratio should be less than 1. Okay. Now here, if the ratio sigma AC upon sigma AC cal divided by sigma AC is less than 0.15, then you can take directly. So interaction कैसे रहता है हमारा? General interaction ratio is what? So we have got sigma AC calculated. ये कैसे निकाला हमने? P by A. Then sigma AC permissible, we got from L effective upon R minimum. It depends on L by R, exactly compression member design from that table. Then plus sigma BC cal, which is nothing but M upon Z XX. And then there is a sigma BC permissible, which we get it from L upon R minimum, D upon T, T upon T, and D1 upon T. It depends on that, and the table 6.1. This ratio should be less than or equal to 1. If this is satisfied, that means your design is safe. समझ में आया सभी को?
Yes, sir.
Because your column is carrying axial stress. So this left term is axial stress and this is a bending stress term. As both forces are there in the member, we are taking the interaction. So we know that in column design, we generally take the interaction, even RCC structures also. Now there is one more point which is missing here. That column carries biaxial moment also. Don't forget that. There is a possibility that column will carry biaxial moments. Let's say this is your plan of the column. This is your plan of the column. It is connected by the beams. So this beam will have a bending moment here in this column. So due to this bending moment, if I draw the bending moment diagram like this, for example, इसका bending moment निकालता हूं मैं. Yeah, this is my frame. This is my bending moment diagram. And this is my column bending moment diagram. If I draw cross section like this, section A. Now, let's say this value is 20 kilonewton meter, for example. There is axial force in the column P, let's say any value you can take. And if I draw section in this direction, let's say section BB, and let's draw the frame here. In this direction, I want to draw the frame here. There will be bending moment diagram in this direction. So let's say if I say this beam as a B1, so this is your B1. Column are same. Let's say this is your C2, column C2, column C1. And let's say this is your C4, C3. So this column is C1, this column is C2. Here this column is C4 and this column is C2. And due to the load, there will be bending moment like this. And like this. Let's assume this bending moment मेरा समझो 50 है column में. Okay, this column is having 50 kilonewton bending moment and there is axial force also P. Now there are two moments in the same column. One is 20 kilonewton meter. So tell me if I say that this is my x axis and this is my y axis, 20 kilonewton meter, is it mxx or myy? बताओ.
MYY. MYY.
myy, because this is axis is y and about that axis this moment is there. So this is your myy. We can call it as a minor moment also because it is about minor axis. The minor moment. And then what is this 50 value? It is like this. About x axis. So this is mxx, which is major moment because it is about major axis. You know major axis, minor axis. So major axis or major moment here. Getting this? समझ में आ रहा है सभी को?
Yes, sir.
That means your column is carrying two moments and one axial force. So what you will do, you will calculate the axial stress sigma AC cal. This is very clear, which is P upon A. Then you will calculate sigma AC permissible, which depends on L upon R only as per compression design. It depends on this. Then you will calculate sigma BCX, which is MXX divided by ZXX. Permissible value sigma BCX depends on L upon R minimum D by T. क्या था वो D1 by T and और क्या था T upon T. And sigma BCY will be MYY divided by ZYY. Then permissible depends on the same parameters. This one, all same parameters. And finally, we have the interaction ratio sigma AC cal divided by sigma AC permissible plus sigma BCX divided by sigma BCX permissible plus sigma BCY. This is cal. Cal means calculated. And this is sigma BCY permissible. Should be less than or equal to 1. Got this?
Yes, sir.
If this is satisfied, then your design is okay. Now there is one more term actually they have given. Just refer this study material. It depends if your sigma AC cal divided by sigma AC ratio is less than 0.15, then you can use this. So whatever I told you now, it depends. If sigma AC cal divided by sigma AC permissible is less than 0.15, first you need to calculate this, only this ratio. If it is less than 0.15, then you can use this formula. And if it is more than that, then you can go with this formula as per the code. So this CMX and all these parameters are given here. You just refer this. This is self-explanatory. And you put the values. Got it? So I hope all of you got the design concept of the design of beam column.
Yes, sir.
Now homework for you. So you take any example of beam. You assume certain load. So one problem is this. Let's say you are having a beam of span 6 meters. The load is 10 kilonewton per meter. Assume this as a simply supported. Design this beam. You can take beam sections as I sections. Second problem is you need to design the beam, but in this case now the same beam is there, but it is a fixed support. Span is same, load is also same, but it is a fixed beam, design beam. Then you take one more problem of the beam column design. So in beam column design, let's say this is your fixed support. Let's say this height of the column is 4 meters. The span of the beam is 5 meters. Load on the beam is 10 kilonewton per meter. So analyze this frame using Staad Pro software. Get the bending moment diagram and design this column. Definitely it will have axial force and it will have a bending moment. Or additionally, I can say, let's say this is your space 3D structure. And also put the load here as some 5 kilonewton per meter. So load is different. Span is same. You can assume this span as 5 meter itself. But as the load is different, then both moments will be different actually. Biaxial moments are different. And design this column. So it will have mxx, myy, and axial force. So this is homework to all of you. You follow this PPT. The steps are very easy. But whenever you take this, what is x-axis, what is y, there is actually a trick or understanding. So understanding is not in the steps of the design, but it is understanding the mxx, myy, then L effective values, how to calculate that, what is R minimum, and so on. So these are the concepts where many times the students or candidates do mistakes. So in general, I have told you, all of you, that structural engineering is very easy, provided you know the concepts, fundamental concepts. The procedure of design is always easy and same. The behavior of the structure is maybe difficult to understand in the beginning. So any questions? Yes, got the concepts?
Yes, sir.
बाकी किसी को क्वेश्चन है क्या कोई?
Sir,
स्टील
Yeah,
स्ट्रक्चर्स
yeah.
में सर जैसे हम लोग सर
Mhm.
जैसे दो स्टील मेंबर को अगर ज्वाइन करना है तो सर उस केस में सर कनेक्शन मतलब स्टैड प्रो में कैसे देंगे और वो
नहीं.
चीजें सर वो कैसे होगा?
See, connection Staad Pro, you know that by default it is a fixed connection. Member to member, you are asking.
So if we connect the members through like plates and bolts, then in actual we connect like that steel members. But in Staad Pro, how we will going to get such a thing? That's my
Staad
doubt.
Pro, say, let's say this is a frame, for example. Yeah, yeah. So let's say this is your frame. If you don't tell Staad to do anything to this part, then it will be by default a rigid joint or fixed joint, we can say. Rigid joint, which is fixed joint. Staad Pro will automatically analyze this and it will give bending moment like this. Okay? By default.
Yes, sir.
Now, let's say as an engineer, you feel that I don't want this to be fixed. Then you know instead how to release the moments. पता है ना?
Yes, sir.
Then in that case, in Staad Pro, I will tell the Staad Pro, please release this moment, start moment and end moment. All moments I want to release. Then you will see the bending moment diagram like this. And as this is the bending moment diagram, there is a release to the beam ends. Definitely there will not be any moment in the column. कॉलम में मोमेंट क्यों आता है? ड्यू टू द बीम मोमेंट्स. दिस बीम मोमेंट ट्रांसफर्स इनटू द कॉलम. This moment gets transferred into the column. So we get the moments in the column due to beam end moments. And if you release this, there will be only moment in the beam and not in the column. In column, there will be only axial force. Getting this? So we are telling the software to release the moments. So this way we can ask the software what kind of joints you want, rigid or simply supported joints. Got this? How to tell the STAD?
Yes, sir.
ये समझ में है? And second, detailing part, I think we had covered that in conceptual design. फिर भी करेंगे cover एक बार. So now if you want, समझो ये column है मेरा. ये this is my beam. Right. Forget this part for the time. Then there is definitely there is a vertical flange of the column. I section is है समझो इसे. There are two flanges here to this. Then two flanges to this. And also we have a flange to the beam. Now we need to decide what connection I want. Let's say I want this connection to be fixed connection. So as there is a fixed connection, you know that at the top there has to be tension. The tension will develop if it is a fixed connection, and that tension will transfer into the column. When I say it is a fixed connection, that means the column also carries that moment. You can see from the bending moment diagram. If I say this is a fixed beam, definitely this moment has to be transferred in this column. Then and then we can say it is a fixed connection. If you are transferring this moment into the column, then I can say it is a fixed connection. So how can I transfer the moment? So we transfer the moments means we transfer the forces which are generated in the beam. So if I say it is a fixed beam, you know that this is your bending moment diagram. So there will be tension here. There will be tension here in the top fiber of the beam. There will be compression here, right? So this tension has to be transferred here in the column. So we generally put one horizontal plate over here. ऐसे plate लगाते हैं. Okay. So that will transfer to this. Then in the compression side also we provide one plate here. And if the depth of the beam is more, then we can provide diagonal plates also, stiffeners which are there. Now this is your fixed connection. Now this tension will transfer into this column. There will be tension here and there will be compression also here in the column. So this T into C into D and this T into C into this D means there will be moment transfer in the column. This is your fixed connection. So if you assume in the analysis this case, then you need to detail in reality like this in drawings and on site also. Now let's say you want to consider this beam as a simply supported. अभी मैं काम करता हूँ. ये half portion, let's say this is your fixed connection. And in this half portion, I will show you the simply supported connection. Simply supported or hinge. So you know that when I say it is a hinge or simply supported, that means there is zero moment. When I say it is a zero moment, it will not transfer into the column. Okay.
Yes,
so if you don't want to transfer, then don't provide the plate over here. First point. Second point, the tensions transfers to the flange. Right? Tension flange में तैयार हो रहा है ना? That it will transfer into the column through flange in this line. So what I will do in this case, I will not provide the flange in this zone because I know that if I connect it to the column, then it will transfer the moment and tension. So I will cut the flange over here. I'm cutting this. I will also cut the flange at the compression side. So now whatever tension is getting developed here. We, as there is a gap, that means agar if that there is a tension formation here, possible tension formation, it is not going here. As there is, it is not going here, then it will be zero. It will not develop itself because it will try to go and it will, there is, as there is no connection, it will automatically become zero or near to zero. And we are only connecting this beam to the column through only web. That means we are only transferring the force, which is shear. So shear is transferred directly here. That reaction we can say, which is transferred through this bolted or welded connection through web only. So I'm not connecting this flange to the column. So this is your simply supported connection. I hope you got the concept. Right?
Yes, sir.
This way we can handle. So Staad doesn't understand what connection you are designing. You have to decide that I want this rigid joint. Then we can tell the Staad, please analyze this. As an engineer, if you feel I want this hinge joint, then tell the Staad, release the start and end, give me the forces and moments. I will design it and I will detail like this. So that is the way we do it practically.
यस सर, यही कंफ्यूजन थी एक्चुअल में। मतलब जो रियल कनेक्शन होगा वो डिटेलिंग में शो करना है, और स्टैड में हमें मूवमेंट रिलीज या रिजिड जॉइंट रख के उसको प्रॉब्लम सॉल्व।
राइट राइट, करेक्ट करेक्ट करेक्ट।
यस सर,
यस यस, रिलीज दिया तो मोमेंट नहीं लेगा. So the analysis we decided by joints. So analysis के लिए सिर्फ उसको बताना है कि हाँ मोमेंट लेना है या नहीं लेना है. If you don't want moment, release it. If you want moment, don't do anything. It will automatically take fixed connection.
यस सर.
Same cases at the bottom. अगर supports भी many times we may require simply supported means supports as a hinge supports. So in that case, what can I do? I will, in Staad Pro, I will consider the hinge support like this. As it is a hinge support, you know that अभी ये column का क्या होगा? Let's say I am only considering this part as a hinge support. Right is fixed support only. So I know that there will not be any moment here, so it will be zero. So my bending moment diagram will be like this. ऐसे रहेगा. Right? This support I am giving in the Staad Pro software.
यस सर.
Yes, Sulekha, you have any questions?
Yes, sir. Sir, when we calculate the L effective value, yesterday we told about it depends upon the support conditions. Support conditions like fixed, both and fixed, then it will be 0.65 L. But now in the explained problem, we consider 0.85 L. Then why it is different?
0.85, you take little higher side actually. Practical purpose, we don't take 0.65. We take little higher side, which is comfortably 0.85 is good number. Okay.
So always we take 0.85?
0.85 for fixed connections.
Okay.
So you are on the higher side when you consider 0.85. Yes or no? Design will be on the higher side. Why we take? Because 100% fixity is really not possible in practical structures. Practically 100% fixity is not possible. Okay. And practically 100% hinge is also not possible. So fixity में थोड़ा सा margin ले रहे हैं. We are taking 0.85. So I think code में भी 0.85 दिया है कि नहीं? Let me check it. 0.65 तो दिया है, but so there are some recommended values they are giving some. यहाँ दिया नहीं है, but I think in some code it is given recommend. Actually, they are giving recommended values also.
In IS 456 it is given.
It is given. But 0.85 we generally take for RCC structures also and for C structures also. The more conservative approach is directly take L. More conservative. Because what happens, why we take on the higher side? If I ask you why, you are asking me the question why we are not taking 0.65 and why 0.85. 0.85 is safer approach or unsafe approach. There is 0.65. So who is safer, this one or this one? Safer approach क्या है?
0.85.
This is safer approach because L is more in this case. So now when I choose safer approach, say as a structure engineer, many times we choose safer approach. Can anybody tell me what is the reason of this? Sometimes even the code or any book is saying you take this value, still I take this value. Why I am taking safer approach? कोई बता सकता है?
Yes,
Already हाँ.
insight maybe it is not
Right.
constructed.
So whatever you assume in the analysis or on the paper, you must assure that it will be achieved on the site exactly as it is. And that's why I told you 100% fixity is really not possible on site. Even in drawings also, we are giving, see, if you say, I told you first that I don't want to connect this to this member, I don't want to connect this, but still I am connecting this using the web, yes or no? This web is connected and this web is also having certain depth, yes or no? That means this smaller depth will also offer some moment of resistance. That means it is also not 100% hinge connection. So this is always there in real structures. In RCC, it is very high actually. The assumptions are very high. That's why the factor of safeties in RCC structure are more. Because whatever we say, it is not achieved in concrete structures. The assumptions of fixity, assumptions of hinge connections in concrete is very difficult. And that's why we are having more factor of safeties in concrete structures. In steel structures, that is less. We are near to the reality. So in this case, this D is very less. So it is near to the hinge structure. But still, I am saying it is near to the assumption. Near to the assumption. Whenever I say near to the assumption, still it is not exact. So I think we have learned in the mathematics, limit tends to 0. I think you remember, पता है integration ये सीखा था हमने कभी.
Yes, sir.
X tends to 3. Limit x tends to 3 means it is tending to 3, means it is not exactly 3. Let's say this is your 3 number line. So your values are somewhere here, near to 3, but not exactly 3. Near to. So it depends. Let's say this is your analysis line. For example, I'm just giving some arbitrary example. Yeah, analysis ka line hai. That is means whatever you are doing in the office, in the Staad Pro, your assumptions, everything. This is analysis and assumptions, we can say. Done in the office, on the paper, in the softwares, whatever. Now, one engineer is designing the structure, preparing the drawing, and his number is coming here. So that means there is a disparity from the analysis, and this is your real condition on site. So there is a difference. Let's say this difference is, I'm just giving some, this difference is 10%, or let's say 20% difference is there. That means it is away from the analysis assumptions by 20%. One engineer is designing one structure which is having 5% deviation from the reality. Now tell me who is the best engineer? This 5% wala ya 20% wala best engineer? Who is the best engineer? The number 1 engineer, number 2 engineer. Question समझ में आएगा? What's the question?
Number one is
Number 1 ही रहेगा ना, number 1, because see, he is more closer to the reality. His assumptions, his design, his analysis, his drawings, it is closer to the assumptions which he has considered in the beginning, in every stage of the office work, whatever he is doing, analysis, design, drawings, modeling, everything. Say you assume this 0.65, but you know that in reality the fixity is not 100%. That means this assumption is not correct. So why not to go for the assumption which is nearer to the reality? And that's why we go for the higher side here. And whenever you are in doubt, go for the higher, safer approach always. समझो ये सब किसी को समझ में ही नहीं आया concept मेरा कि अरे क्या 0.65, what is this 0.85? Then I will say the person who don't know, at least he should know that 1L is a really good approach. So L effective will be 1 into L. छोड़ दो ये कितना लेने का. This is a more safer approach because he is having less knowledge. So the person who is having less knowledge, less confidence, less experience, they should go for the safer approach, more safe approach, we can say, more and more. Those who are experienced, so abhi I go in this case, but in any case, even though I am experienced and even though this person is not having knowledge, I will not go for this approach. This is nahi, matlab, this will not be followed on site. So in structural engineering, actually this is the tricky thing generally where the people find difficulty in understanding. But yes, you will understand slowly through experience, through thinking over the problem in a different, we can say, way in all directions, and look at the problem by integrated approach. Integrated means every phase, whatever we have, analysis, design, drawings, site conditions, look at the problem in all aspects from all the phases, parameters all together, and take one common decision which is a good, which will take care of all the parameters. Still that engineer will have 5% error, definitely yes, 5% error to hoga hi hoga usme. Whatever may be the experienced person, he will not at all reach to this green line, which is a reality. Reality achieve karna structural engineering mein is not possible. Yes, we can have a safer structures, but we cannot have exact structures as we think, just not possible. They will not behave. Nature will behave on its own. Human will behave as his mindset and his knowledge. So ye error to hoga hi hoga. The error should be on the higher side. So safer side mein hona chahiye error. That is the only thing you should consider. So according to your experience, you can take the decisions now once you understand this. So don't give stamp to anything whatever you learn. अभी तक जो ट्रेनिंग में सीख रहे हैं आप, you learn the basics, you are learning the softwares, you are learning a lot of knowledge actually in structural engineering, but don't stamp it. Learn it. For example, I am giving you this guidance on this design of beams, columns, but there will be certain thing which is missing. There are certain things where there is a question, there is a doubt. Definitely that is there. You think over that. After thinking, come with some solutions and some questions, and you can ask the questions again to us. So it is a continuous process, asking the questions, getting the solutions, again asking the questions. So that is the learning. So why is very much important in anything, to in learning process especially. Ask why, ask why, ask why. See, at the end, definitely you will not find the exact answer. Ye to, even though you are having 40 years of experience, still that final answer, exact answer, you will not get. Only the error, this error will be less. So you will be more near to this. That is the only experience. So I say समझ सकते हैं कि the beginner will have 20% error away from the reality. And as an experience, I am 5%, let's say. So what I achieved in my career, throughout my career till now, I only got 10% extra. But still I am not getting 100%. So yahi hai, matlab, this is the case. So you should be open to understand such kind of things in structures. And so there are two possibilities from your side as a student or candidates कि अरे एक तो एक आपको difficult लगेगा, there is one point कि यार क्या है, बहुत ही difficult है something. How to understand this? Because we are used to understand the things which are exact. For example, I will be happy if I understand 2 into 2 is 4, because this is having exact answer. But if I ask you 2 into 2 is near to 5, then you will be in trouble. So some person will say 2 into 2 is near to 4.5. Some person will say 2.2 is equal to near to 3.7. When there are many answers to the same question, then there is a problem. That's why we many times find difficulty in understanding. But generally, I say this is a really good thing in reality. In life also, you will never find anything. See, we don't find truth or reality exactly. I think you know that we are most of the times as a human being in illusion. See, something it is out of technical part. Most of the times we are in illusion. We imagine certain things, we precondition our mind, and then we give the answer to that. Whenever you precondition, it is a illusion. It is not truth or it is not reality. But that is the life. So such kind of errors will always be there in life, in technical world or any world you are staying. It is always there, and that's why it is beautiful also. Means why human being is having beautiful life due to this. So I generally say this is nothing but an art. Art is very organic actually in nature. It has no exact or organized way. If you see the trees, if you see the people, if you see the people are constructing the construction, there are trees, there are some universe also you'll see. It is organic in nature, organic. Whenever I say organic, it is not having any symmetric or we can say there is no exact thing to that. If you see the tree, the branches and everything, they are coming in any direction, in any shapes. So in totality, it is having a, we can say, harmony in them. In totality, the harmony is due to their organic and erratic nature. So in the similar fashion, in structural engineering, due to its erratic or different answers which are away from the reality, it is having that artistic way, and the harmony is there within that. सबको समझ में आ रहा है? कुछ तो ये हो रहा है क्या? नहीं ना? Are you getting? क्या बोलना है मुझे? So the structural harmony is there, that it is not having exact answers. So in every art, you will find the same thing. The greatest person in any field, that is the thing. A musician है, singer है, structural engineer है, civil engineer है, or he may be artist, painting, करने वाला artist रहेगा, कोई भी रहे, photographer. This is the same thing. So I hope this gives your answer. See why I'm giving you this example, because you will get such kind of questions many times in structural engineering. So you can pause little more time, just think over it in this aspect, and then you will find the answers. So it is not always that you will get the trainers or guide to give you the answer of each and every question you get, and you should not expect also to that level. After some time you should become the mentor of yourself. आप खुद ही आपके गुरु बनने चाहिए. That is the final destination. So definitely we require teachers, gurus in our life just to show you the path, not the final destination. You have to go to your final destination on your own. At some point you will become the teacher of your own. So that is the final aim. So apart from our technical knowledge, I would expect this also from you in your future career slowly. If you always require mentors and guide at every phase of your life, either technical or your general life, then you will become handicapped. And then handicap is not good thing, you know. So these are the things. I'm not saying that you don't ask questions in the training program. वैसा नहीं है, please. Try to understand my intention in this. Definitely in the training program, you must ask maximum questions as possible. Whenever you are in learning phase, you must ask maximum question possible. But during that process, you also develop your own thinking. Okay. So you do the homework. So shall we close the session?
Yes, sir.
Okay. So thank you all and good night to all.
Thank you, sir. Good
Thank
night,
you,
sir.
sir. Good night, sir.
Thank you.